This video is about exotic stellar objects, or exotic stars. Neutron stars are probably the most well-known type of exotic star. They're formed when a star much larger than the Sun exhausts all the elements in its core, from hydrogen to iron, by using them all up in nuclear fusion and creating layers inside the star of different elements. Once the star reaches iron, it can no longer continue to support itself because iron has no energy to give in nuclear fusion. This causes the star to effectively stop giving out energy. And when this happens, gravity begins to crush the star back down. The core of the star, or the center of the star, shrinks as the outer layers fall onto the core and are blown away in a massive explosion called a supernova. The core of the star is severely compressed. A ball of matter much more massive than Earth, more massive than the Sun, is compressed into a sphere about the size of a small city. Because of how heavily it's squeezed in, all the atoms inside the core have their particles, so their protons and neutrons, all being crushed into neutrons. That's why they're called neutron stars. These stars have very powerful gravity, so strong that it can actually bend light around itself. Not to an extent that light itself falls in, like with a black hole, but enough that we can actually see parts of the neutron star that we would not normally see with another weaker body like a regular star. And they're also much hotter than regular stars. The types of quarks that are important here in the context of strange stars are, of course, strange quarks, which I mentioned before, and up quarks and down quarks. The two particles that make up the nucleus of an atom are up quarks and down quarks. A neutron is made of two down quarks and one up quark, and a proton is made of one up quark and one down quark. Of course, inside a neutron star, everything is compressed into neutrons with an ocean of electrons flowing between all of them. However, inside here, inside a quark star, some of the quarks could actually be turned into strange quarks because of the extreme temperatures and conditions inside the star. Strange quarks have very different properties from regular quarks that make up protons and neutrons. Strange quarks could possibly create a type of matter called strange matter, in which the star actually comes to be, or the inside of the star at least, comes to be dominated by this new form of matter. Strange matter has completely different properties from what we are used to interacting with. It is possibly a very stable form of matter because it's completely dense and basically invincible. Strange matter is so corrosive that if it actually comes into contact with, if it touches regular matter, then it would immediately convert that regular matter into strange matter. Now, since strange matter is much more dense than normal matter, if it were to come into contact with something made from normal matter, like for example, let's just take an asteroid floating around in space. That asteroid would actually shrink down to a very small size as it turns into strange matter, because strange matter is so dense. And this brings up to the second type of strange star, which is simply a regular star that gets hit by strange matter. Normally, if any type of regular matter were to approach a star and were to actually come into contact with it, it would basically be vaporized by the star because of the extreme heat. Strange matter, however, and basically any matter inside neutron stars, are so unbelievably hot that a star, even the hottest stars in the universe, seem cold in comparison. So these strange matter droplets, called strangelets, could actually come into contact. If one were to come into contact with a star, it would actually be able to hit the star directly and convert all of it into strange matter. The star would still keep all of its mass. It would not be reduced in its mass, but it would shrink down to a much smaller size and as a result become much dimmer. And for that reason, we can't really find a strange star if they do exist. Strangelets could be released into the universe in an event called a kilonova, when two neutron stars come near each other and end up colliding. We don't know if these droplets exist. So far, we haven't found any, and we certainly haven't found any stars that have been disappearing in the last 1,000 years. So I highly doubt we'll be finding any stars that keep disappearing from strange matter droplets in the next 1,000 years. So since we really haven't found any stars that seem to suddenly be shrinking down and disappearing, I doubt these droplets exist in any in a high enough amount to actually have a major effect on the universe. But the possibility is still there. And then, of course, the last type of neutron star is called a Blitzar. A Blitzar is a pulsar that has enough mass to technically has enough mass to collapse into a black hole, but does not because it's rotating so fast. It's rotating so fast that the force from the rotation is actually able to counter that gravity and prevent it from collapsing. Of course, this does mean that once the star finally does slow down, it becomes a black hole. Population 3 stars are a theoretical type of star that existed when the universe was much younger, only a few hundred million years after it was created. These stars are not exotic in the sense that they're made of different types of matter or they have radically different conditions from regular stars. Instead, they're exotic in the sense that, first, we haven't actually really found any of them. We do know that they exist because population 3 stars, the basic definition of them is that they are simply the first stars, the first generation of stars to have ever been created in the universe. So we know that there was a first generation of stars in the universe. We simply haven't really found them yet because they're so far away that their light hasn't reached us yet. These stars were created in a time when the only elements, the only atoms in the universe were hydrogen, helium, and a very, very tiny amount of lithium. And as a result, modern stars have high amounts of what is known as metallicity, which is simply the amount of materials that are the amount of elements that are heavier, that are beyond hydrogen and helium. And population 3 stars didn't have those. There was, as I said, a very, very tiny amount of lithium, but it was so small that it was largely inconsequential. These stars were made entirely of hydrogen and helium. And this is important because modern stars, due to their higher content of metals in this situation is simply anything more heavier than hydrogen and helium. Modern stars, since they have higher amounts of metals, that can actually keep them from growing to much larger sizes. However, since these stars had no metals in them, they grew to absolutely enormous sizes. And this was only fed further by the fact that the universe back then had a lot more raw materials for stars, raw gas and dust. 4 stars because none of it had been used up by anything yet. So these stars were much larger and hotter than stars that exist today. They were equal to or larger than the largest stars in the universe today. But because of that, they also lived for a very short amount of time, for only a few million years at most. And and once their fuel ran out, they exploded in massive supernova, which, with little doubt, would have been much larger than the than supernova explosions that occur in the universe today. And they distributed the first large amounts of heavy elements into the universe. A quasi-star is a hypothetical type of star that existed during the population 3 era. These stars are no longer possible now. They only could have existed back then. And to understand what these are, we need to know what protostars are. Protostars are basically a star before it begins nuclear fusion. When a star is first forming from a cloud of gas and dust, the gas and dust, as it clumps together, can reach extremely high temperatures, and eventually they get to a point where they reach a critical temperature point where the process of nuclear fusion can finally start, and a star is effectively born. Those protostars are sort of baby stars, if you can imagine it that way. Quasi-stars were formed from massive protostars that back then that were larger than many, if not most, stars today. These protostars grew to such massive sizes due to the fact that they only had hydrogen and helium in them, that the core of the star actually collapsed and underwent the supernova process that I described earlier. It went supernova before the star before it became a proper star. And when this happened, these large protostars were actually large enough to have their outer layers absorb the impact of the explosion instead of being destroyed and blown away, like what would happen in a regular modern supernova. Once that happened, of course, since these cores were very massive, they didn't form neutron stars, they simply collapsed into black holes. And what this created was what was a quasi-star, what's also known for this reason as a black hole star. These stars were ridiculously massive, much larger than even the largest stars that we know today. And they were powered not by the process of nuclear fusion, but by actual, true black holes. These stars did not live for very long before the black hole simply consumed the entire star, but they did actually live for a few million years or so. Because although black holes do consume anything that comes too close to them, they also do put out a lot of energy outwards, and this would have been enough to sustain the star for a short amount of time before a black hole simply consumed the star and ate it up. These black hole stars are also a possible explanation to the supermassive black holes that dominate galaxies today. Supermassive black holes being the massive black holes in the center of modern galaxies. And this is one of the possible explanations for their origin. A blue dwarf star is a star that could exist in the distant future of the universe. Blue dwarf stars are an evolution of red dwarf stars, which are the smallest and longest living stars in the universe. Red dwarfs are actually the most common type of star in the galaxy. We just can't see them because they're too small for us to see, though we can detect them with large astronomical telescopes and space telescopes. A blue dwarf is simply a type of star that could exist after a red dwarf star uses up most of its hydrogen. Not all of its hydrogen needs to be used up for this to happen, but simply a large enough amount. And this is because stars grow hotter and more luminous as they use up their fuel and age. None of these stars exist yet because blue dwarf stars are so long-lived that the universe right now is not old enough for any of these stars to exist yet. And by the time these stars do exist, most stars in the universe, most non-stars in the universe that are not red dwarf stars right now, will have long since died off, used up all their fuel, and either gone supernova or met the fate of our sun, where they expand outwards, shed their outer layers, and become planetary nebulas and white dwarfs. These stars could eventually come to be the dominant type of star in the universe. These stars aren't exotic stars, again, in the sense that we may think of being of having very different conditions or being made of different types of matter, but they're simply stars that don't exist yet, and they could exist in the future, being an evolution of a type of star that exists right now. An iron star is probably the most exotic type of star that in this video, not necessarily from a viewpoint of being interesting or having the most alien-like conditions, but simply from a perspective of being the most different from all the other stars here. And that's because an iron star is not a conventional luminous star. It doesn't really shine, because these stars are basically what would happen to objects like white dwarfs and neutron stars in the very, very distant universe. After every last star, even the red dwarfs, which eventually become blue dwarfs, even after all the blue dwarfs have used up their fuel and burned out, these stars are the last true large physical stellar objects that will exist in the future. The last physical objects that we could touch, because we can't really touch black holes. And iron stars are simply stars that are formed by a process called quantum tunneling, which is far too complicated and long for me to explain here, but this process could create a sort of cold fusion, which is simply nuclear fusion at low temperatures, or at least from much lower temperatures than when it normally occurs. And this would turn all the atoms of a star into, or of a stellar remnant, into iron 56, which is a very stable element. This is, however, presuming that protons, the subatomic particle that I discussed earlier, do not decay. There is a current theory in astrophysics called proton or decay, which says that at some point in the future, protons, which are one of three particles that make up atoms, might actually end up decaying. We don't know if this will happen yet. We have not seen any protons decay so far. But if they do actually fall apart into the particles that make them up, then this means that at some point in the future, before iron stars exist, all matter in the universe would basically dissolve away into really probably the most basic particles that exist, meaning that matter itself will no longer be able to exist. But since this theory is not confirmed, we don't know if it will happen. It may not happen. And if it doesn't, if proton decay theory is false, then iron stars will eventually become the dominant objects in the universe. These stars will simply be cold spheres of iron. That's it. There'll be nothing interesting about them. They'll just be big, large balls of iron floating in a universe that is dominated by iron stars and black holes. A completely dead universe with no activity remaining of any kind.